So now let us evaluate the grand partition function for the Bose Einstein and Fermi Dirac case. As I told earlier in the last class, the determination of partition function is not easy for Bose gas and the Fermi gas because of this condition. Sigma I Ni equal to capital N, the total number of particles in the system. Okay, because of this condition, partition function cannot be easily evaluated for the Bose gas and the Fermi gas. So we consider only the grand partition function. What is grand partition function? We know grand partition function is this. Sigma n equal to 0 to infinity set to the power n. And here comes the, what is this? This is the partition function. Okay. This term is the partition function. We know the grand partition function is, this is the partition function. This thing is the partition function. And the grand partition function is, as you know, it is this. This is the grand partition function of the system. Sigma n equals 0 to infinity z raised to n, and this term is the partition function. So we give the partition function here. Okay, sigma n epsilon equal to n. This is the summation over different distribution sets e to the power minus beta, and this is the energy. This is epsilon into n epsilon. Epsilon into n epsilon. Okay, and as we did in the case of Maxwell-Boltzmann case, this actually consists of several terms, sum of several terms. That can be written as a product of this. So while writing this product, we have taken this set into this. Why? Because we know we are taking product of set to the power n epsilon, set to the power n epsilon over all single particle states. So when you take that product, you will have n1 plus n2, n3, I mean the different single particle states. So when you add together the power of set, when you take the product, you will be getting set to the power, that sum will be equal to capital N, because you are taking sum of the different number of particles in each different states. Okay, so I can take this set inside this. So what we have is a double summation. Okay, first over the numbers n epsilon, first over the numbers or the different distribution sets of n epsilon constrained by a fixed value total number n. Okay, this is the constraint, this is the restriction, sigma epsilon n epsilon equal to capital N. Okay, constrained by fixed value of the total number n, and then the second summation, this summation over all possible values of n. Okay, so we have a double summation here. And they say this is equivalent to summation over all possible value of n epsilon. Okay, so very important idea, this double summation, first over the numbers n epsilon, okay, constrained by fixed value total number n, and then over all possible values of capital N. So this is equivalent to summation over all possible values of n epsilon independently of one another. Okay, so we are making a transition. We are writing this in this form, this product over the different single particle state, that is written in this form, set e to the power minus beta epsilon 0 and 0, set e to the power minus beta epsilon 1 and 1, this product. So that product is written here. And the summation, this summation, these two summations are what? Summation over n0, summation over n1, summation over n2, independently of one another. Okay, so this product is written here. Set e to the power minus beta epsilon 0 and 0, the first single particle state. Set e to the power minus beta epsilon 1 to the power n1, the second single particle state. See the product over the different single particle states. So that product is written here. And then this double summation appearing here, that is written as what? Sigma n0, summation over n0, summation over n1, summation over n2, like that, independently of one another. Okay, I think you have understood it. So this thing is written sigma n0 set e to the power minus beta epsilon 0 n0, because n0 is applicable to only this. Sigma n1 set to the power e to the power minus beta epsilon 1 to the power n1, so on. Okay, so a product, and that is written pi epsilon. Okay, sigma epsilon. Okay, pi product. Pi stands for the product. So product of this sigma n epsilon set e to the power minus beta epsilon to the power n epsilon. Okay. So this summation sigma n epsilon extends over possible values of n epsilon. Possible values of n epsilon. The possible values of n epsilon are 0, 1, 2, 3, etc. for the Bose gas, because Bose gas particles do not obey Pauli exclusion principle. So n epsilon is 0, 1, 2, etc. for the Bose gas. And for Fermi gas, we know it obeys Pauli exclusion principle. So a level can be occupied by at most one particle, maximum one particle. So 0 or 1. Okay, so for Bose gas, this thing, the grand partition thing for the Bose gas is this pi epsilon, the summation over n epsilon, that is written like this, summation over n epsilon, you know, it is 0, the first thing is 0, then the next term is 1, next term is 2, okay, so it is written like this, e to the power 1 plus z, e to the power minus beta, epsilon, okay, eta epsilon to the power 1, okay, then to the power 2, to the power 3, etc. So we have this pi epsilon 1 minus z e to the power minus beta epsilon. See, okay, pi epsilon is a product over the different single particle states. And for the Fermi gas, it is 1 plus z e to the power minus beta epsilon, because here you will have only two terms, n epsilon equal to 0 and n epsilon equal to 1. Okay, n epsilon equal to 0 and n epsilon equal to 1. Only two terms will be there. Okay. So pi epsilon 1 plus z e to the power minus beta epsilon. You might be wondering, what is this epsilon, the product over the epsilon? It is the different single particle energy levels, energy states. We have to take the product over the different single particle energy states. Okay. So for the Bose gas, this series is 1 minus z e to the power minus beta epsilon to the power minus 1. Sorry, minus 1 is missing here, minus 1 is there, because you are converting this series into this form. So minus 1 is there. 1 minus x to the power minus 1 is 1 plus x square plus x cube. So we have that form here, 1 plus x square, x cube, like that. So 1 minus x to the power minus 1. So sorry, a minus 1 is missing here. Minus 1 is there in Fermi gas. So for the generally you can write it like this: pi epsilon, the grand partition function. The grand partition function is pi epsilon product over the single particle states of 1 by z e to the power minus beta epsilon for the Bose-Einstein case, and pi epsilon 1 plus z e to the power minus beta epsilon for the Fermi Dirac case. Okay, so the Q potential, if you take the Q potential is log of the grand partition function. You have to take the log of it. So when you take the log, you have to take the log. So when you take the log, you will get minus term here, because you have 1 by 1 minus z e to the power minus beta epsilon. So minus, the product becomes summation when you take the log, minus sigma epsilon log 1 minus log 1 minus z e to the power, okay, minus sigma epsilon log 1 minus z e to the power minus beta epsilon, and plus sigma epsilon log 1 plus z e to the power minus beta epsilon. Again, there is small mistake here. This is minus plus here. Okay. So this is the Q potential. Okay. So minus sigma epsilon log 1 minus z e to the power minus beta epsilon for the Bose-Einstein case, and plus sigma epsilon log 1 plus z e to the power minus beta epsilon for the Fermi Dirac case. So this is the Q potential.